Okay, Coach, I have 7 o'clock. Are you ready to go?
Yep.
Okay.
Good morning. Go ahead. You want to get started? I want to say good morning, good afternoon, good evening to all the people who are welcoming you to ASQ Automotive Division's seminar on the webinar on the multiple overstress testing. Next slide, please. I would really appreciate if everybody stays on mute so that everybody can hear the presenter, John Krucher. Next slide, please. ASQ Automotive Division is with the global division among the American Society for Quality, and we deal with OEMs, the suppliers of the automotive, and everything else. Here is what we will be covering today: the housekeeping items, something about the ASQ Automotive Division, what is our vision, what are the upcoming webinars, and then particular about the multiple environment overstress testing, and we'll end the webinar with the questions and answers. Next slide. So everyone is muted right now. Session is going to get recorded. We will not be any more than 90 minutes. And the downloads of the slides are going to be available on our website, asq-auto.org. And you can ask questions throughout this webinar. You can post your questions, and John Kuchar, the presenter, will be able to see it. And at the end of the presentation, he will be able to answer the questions. So please type your questions in the panel box on your right side of this webinar. Next slide. A little bit about myself. Since July 2011, I've taken the chairmanship role into the ASQ Automotive Division. So I want to take this opportunity to tell you a little bit about myself. I am manager of the global electrification for General Motors in Michigan, in the United States. Basically what that means is that for all the electric vehicles and any of the hybrid vehicles, I'm responsible for the quality. The leadership was, I've been in leadership position in R&D, manufacturing and quality for GM for over 27 years. I have 20 plus years of experience within the quality. I have many different certifications. I'm not going to cover them. And I have been as an invited speaker at different symposium and conferences, including I've been to China to speak at their quality summit, and we have also trained people in Six Sigma and quality management. Next slide. There's a different perception about the automotive as far as an industry is concerned. So this is something I wanted to share with the group, that automotive is still a very growing industry. We are going to have over 1 billion vehicles globally, and these are the pictures you see are from different parts of the world on how many cars are on the road. So if you take all these cars, we can go around the earth 125 times when we are on the equator. So 15% ownership, there is a 3% growth worldwide. So it's a very interesting and very challenging industry for globally. Next slide. So what is American Society of Quality? Some of you may be already familiar as a part of the American Society for Quality. It's the world's leading professional organization and authority on quality. The ASQ is in more than 80 countries. We really encourage you to become a member of American Society for Quality, and then get involved with American Society of Quality Automotive Division. So Automotive Division, we want to be recognized global network for the automotive quality professionals. So if you are in any way engaged with the automotive industry as an OEM, supplier, or any other way, we really want to encourage you to be a part of the ASQ Automotive Division and help us achieve the mission which we have indicated here. Next slide. So here are the key objectives. We wanted to get focused on few very important objectives and make sure that we are having activities and other things which we can do to support these objectives. The first one is to increase the member value. The key purpose for us being here, and myself, Walt Oldak and John Kuchar, all of us are volunteers. So we want to make sure that we increase the member value through the webinars, symposium, and our magazine. So we highly encourage our members to participate in this. And please also provide us feedback on what kind of topics you would like us to cover in the future webinars. So your input is very, very important. We also want to develop the courses for automotive industry. If you're working in medical quality or other things, there are specific certifications which are required for you to work in that industry. Currently, we don't have that requirement within the automotive industry. So we are developing key core 2 competencies, and these are including the PPAP, the APQP, the FEMA, the SPC, and MSA. And we are going to be actually going to have more webinars to cover these core competencies. But the idea is that if your organization would be interested in doing on-site training, ASQ Automotive Division is developing this training, and we can deliver that training to you. Global outreach. As ASQ Automotive Division, this is a global organization. We don't want to be just in the US, so we are looking for any opportunity to participate in conferences, seminars, anything else, training globally. We are already being invited to go and do similar things in Vietnam, China, but any other country, we really would like you to contact us and let us know if you're interested in having us participate in such events. Next slide, please. So here are the last 3. So we have a total of 6 initiatives. U.S. outreach. Currently we have the automotive OEMs which are in Detroit area, which will be General Motors, Ford, and Chrysler, very much engaged with that. Our goal is to get the Tier 1 and Tier 2 suppliers also getting engaged. So please, it is very important that if you are in any of the other areas and you would like to participate more, please contact us. Student outreach. We also are looking down the road because a lot of us have been 20 years in quality. But what is the next generation of the quality professionals within the automotive industry? So we want to work with universities and colleges where we can provide some of the quality knowledge as students are getting out into the industry so that they are more prepared to deal with the quality issues in the practical world. And the last one is to collaboration with other professional societies. ASQ Automotive Division doesn't want to be an island. We want to be all-inclusive. So there are other societies which have also interest in automotive industry. We would like to have joint events with other societies, so Society of Manufacturing Engineers and like Automotive Research. Those are some of just a few organizations which we are trying to collaborate with. So if you are also a member of another organization which will be interested in collaborating with Automotive Division, please contact us. Next slide. I had mentioned previously about the core competencies and the tools which we need for within the automotive industry. Before I use the acronym, so like anybody else, we want to provide you what it really means. So here on this chart, you will see the 5 key quality tools. We really want to make sure that if you're working in the automotive industry, these are the very critical tools you should be making sure everybody in your organization knows. If you need help, especially if you're a smaller organization, we'll be more than happy to provide you the training and with very qualified instructors. Next slide. So we are very happy to provide these free webinars. There's a lot of wealth of information. There are no sales pitch. We are very, very particular that this is the core knowledge. We are providing it to you. Then this is an area also for you to ask questions at the end. So we encourage you to download the presentations after the webinar is done. And I really want to thank Walt Ulrich, who is the key person within the ASQ Automotive division, who has been driver of this webinars. And he also has the presentation from previous webinars. So after you go through this one, and you may want to see what are the other topics we have covered so far. Next slide. So how can you contact us? So here are just some of the information we want to provide to you. You can contact me personally, and I will respond to every email, and I do that. My personal email is asq.automotive@gmail.com. You can also visit our website, and this is a great resource, www.asq-auto.org. We are also very active in the LinkedIn. If you are not a part of the LinkedIn group, the ASQ Automotive Division group, I highly recommend that you can join and use that group to ask questions and use each other's knowledge. We also use Twitter, and the Twitter address is also there. So we really want to use the new media on social media to get our word out and also communicate with members and others who are involved in the automotive industry. Next time. So now I'm going to turn it over to John Krucher. John is an excellent and highly knowledgeable person who has done a tremendous amount of work. I think this is a privilege for us to have a person of the caliber of John Krucher, who has taught for many, many years for the Delphi group, and is highly regarded nationally and internationally for his knowledge in the reliability field. So I'm going to turn it over to John.
Okay, thank you, Kush. First of all, can you hear me okay?
Can hear you great, John. If you want to go full screen for us, that'd be great. Can hear you great, John. If you want to go full screen for us.
All right. How do I do that?
Could be file or something, or probably in view. Yep, full screen mode. Keep going down.
Oh, there you go.
Great, thank you.
Okay. All right. Thanks, Walt. Thank you, Kush. Good afternoon. Hello, everybody. As Kush said, my name is John Krucher. I'm from Delphi Powertrain in Auburn Hills, Michigan. What I'm going to talk about is MEOST, Multiple Environment Overstress Testing. And I'm going to present the topic from the perspective of an automotive component supplier. I work for Delphi in Auburn Hills, as I said. I think you'll find, those of you that have some background in MEOST, you'll find that I'm giving it a little bit of a different slant. And if you are familiar with the method, you'll find that I do hold to most of the rigor of the process, but it is presented slightly differently than those of you that may come strictly from an electronics background. So first, I'd like to acknowledge a few individuals. Steve Schaefer is my boss, who allowed for the time that I took to prepare the material. Bob Fegley, actually performed, he was the test technician that performed many of the experiments that I've done. Francois Coulot is my colleague in France that did one of the case studies that I'm going to present. And Andre Kleiner is my colleague from Delphi Electronics in Kokomo, and some of the graphics in this presentation are his. Okay, so I'm going to start by giving MEOST some perspective. I'll first introduce accelerated testing in general. In doing so, I'll talk about time compression. And then I'll get into basic accelerated life testing, which is, I think, what most people think of when they think of accelerated testing. And then I'll get into MEOST with a couple of case studies. And I do allude to HALT. I just have one slide on it, but I do want to bring it up just to contrast it with the MEOST method that we'll talk about. Okay, so when we talk about an accelerated test, a field correlated accelerated test, normally we're dealing with analytical models. We're trying to model the physics of usage, the physics of damage at the accelerated conditions. The failure modes under those accelerated conditions really need to correlate with our normal usage field failure modes. We don't want any unnatural or foolish failure modes, and the way that one way to tell that you're getting failure modes that are relevant and correlate to what you're seeing under normal conditions is to look at the beta, the Weibull slope, and that should be very, very close to what you see under normal conditions. Now, when we create an accelerated test, I like to talk about it in terms of chasing a particular failure mode. We select our model based on the physics of use, the physics of damage, and we chase after that failure mode. But that doesn't mean that other failure mechanisms are not acting. Indeed they are, but they act at a different rate. So those other failure modes are going to behave at a different rate than the one that we're chasing. So I think the bottom line is we need to keep in mind the failure mode that we're most concerned with. Now, reliability demonstration is done on accelerated tests, but it has the same caveat that any other test reliability demonstration has, and that is that the variation in your parts needs to represent your manufacturing variation. Now, because of the variability in field usage and the environments and the excuse me, and the uncertainty in material constants, we can never come up with a precise model for acceleration. So the best we can hope for is a useful test. So we start with an available test time that is less than our expected product lifetime. So the first thing you always want to look at is time compression. So the two things you think about with time compression, you either remove non-damaging events or you accelerate the number of cycles per time. So the simple classical way to think of removing non-damaging events is validating washing machines. Washing machines might get used anywhere from 2 to 7 days a week. One way to validate that washing machine is to run it continuously. So you have to think about, certainly you can do that, but at some point in time you get diminishing returns, you get other failure modes. Likewise, for another example is if you're testing trunk lids, you can accelerate the number of cycles per unit of time. For example, if you could test a 1,000 cycle trunk lid closure test by cycling it 10 times per hour for 100 hours, or you can do the same thing by cycling it 50 times per hour for 20 hours. So you're accomplishing the same 1,000 cycle test in 1/5 of the time. Now, if you take that to an extreme, you might consider, okay, well, how about if why couldn't I close that trunk lid 8,000 times in 10 hours? Well, certainly you could, and then once again, just like with the washing machine, you need to think about what are you missing. You have to think about, are you heating up the hinge as you do this? Are you allowing for other failure modes that might be important? In fact, they might even be dominant. How about corrosion, for example? So all those things need to be thought about, but I think the takeaway really needs to be, when you start with an accelerated test, you need to start by removing non-damaging time or doing time compression. Okay, so once you take care of that, which is really the low-hanging fruit, the next, maybe the obvious or the more common method for accelerating a test is to run a constant stress test at an elevated level. So we'll talk about that. And I guess to set the stage, well, let's consider a stress strength. It's really a conceptual model. So you have some distribution of customer stress, and you also have some distribution of component strength. And what you need to think about is, where in there are we testing? We're going to test at a very high level of customer stress. Quite often it's 97 percentile, 98th percentile. So I guess the first thing I would ask is, would you expect a higher field reliability or a higher test reliability? And there's a couple caveats. The answer is you would expect a higher field reliability because most of your customers are using your parts in a less damaging way than you are testing them. The caveats are that is not what I just stated, the field reliability being greater than test reliability. That will not be the case if you are missing environments or if your parts do not represent manufacturing variation. Excuse me. And those are two very big caveats. So for the sake of conservatism, and in this presentation I talk about testing at 97.5 percentile. But really you could choose 95th or 98th or some other value. But I'll ask, is it okay to test at only 97.5 percentile? Well, it is, because first of all, if your test has multiple environments, like we're going to talk about here, the likelihood of having extreme exposures for each of the environments concurrently is extremely small. In other words, are you really going to have, what's the likelihood of having 97.5 percentile user for temperature and humidity at the same time? And as you add environments, of course, the likelihood goes down even further. The other thing I'll mention is, we might get very concerned about only testing at 97th percentile or even 95th percentile. I think a lot more mistakes are made by completely missing environments than there are by missing a percentile or two or three here or there when you try to characterize your environment. So I think more failure modes are missed in the field, and we see more warranty problems because we completely miss environments than mistakes made in characterizing the usage at of a particular environment. Okay, accelerated. When we talk about accelerated testing, we talk about an acceleration factor, which is really the ratio of the time to failure under normal conditions over the time to failure under accelerated conditions. And the assumption that I stated earlier, of course, still applies. The failure mechanism at the high stress levels really needs to be the same as what you see under normal conditions. So this is a conceptual model of an accelerated life test. I guess let's start by looking at the blue rectangle, the customer usage level. Now think about that as perhaps your standard test. Think about it also as perhaps the 95th percentile usage of your customers, or the 98th percentile usage of your customers. You designed your test to be that severe. Okay, so if you run your test at that usage level, if you look at on the stress scale and read across left to right across at that usage level, and you get to 1 life, that's a good thing. It means your parts have passed your test, but it may be that you could run on and never get failures, so which is why we like to accelerate tests. So what you might do then is build an acceleration model by testing at higher stresses. So in this graphic, you can see tests being conducted at 3 higher stress levels. At the very highest stress level, of course, the parts are going to fail quicker, and you get the PDF or the distribution there represents a range in times to failure. So each of those PDFs, the 3 PDFs working down, if you think about it, are Weibull plots. Those are life distributions at each of those high stress levels. Okay, so you build your model by testing at those high stress levels. And then once you're complete, you choose a stress model that aligns with the physics of failure. And we'll talk about those in a minute. But when you choose your model, then this allows you to project or predict the times to failure at your customer usage level. So to build this, it does require a bit of work. You know, you do have to run testing to failure at multiple high levels. In some cases, that's prohibitive. Depends on the price, the cost of your samples, and so on. But once the nice thing is, once the model is developed, your validation does not have to be the blue rectangle, if you will, the operating rectangle. It can be one of your accelerated tests. You can select one of the high stress levels and run your parts to failure and have your success criteria for your product to be at some shorter time based on this model. So that in a nutshell is accelerated life testing. The models that are used to project life distributions from one stress to another, that's the curved line on this graph. There are a number to choose from, and you really want to choose one that aligns with the physics of your part degradation. Inverse power law is probably the most common, and there are different forms of that. Coffin-Manson is a very popular common form that works well with thermal fatigue and mechanical fatigue, including vibration problems. For part degradation, part failure that's driven by chemical processes or material diffusion, anything that's temperature driven, Arrhenius works very well. And there are other models. I'm just listing a couple here. Airing models, there's actually several forms of the airing model, and it's really a 2-stress model. So if we go back to, this graphic, if you think of stress as if you think of a second stress acting on this, you can think of a third dimension. So that's the surface gets kind of complicated, but that can be handled analytically using these 2-stress models like the airing model. The airing works particularly well for temperature plus one other stress. So temperature plus a mechanical stress, or temperature plus humidity, and so on. And then the last model that I'm showing here, although there are many more, is a Chemini model, which is temperature and voltage. Okay, so before we get to MEOST, just one quick example of an accelerated life test. This was done on planar oxygen sensor. The business end, if you will, of the planar oxygen sensor is the sensing element. It looks like a matchstick in the bottom left of the slide here. It senses the difference in oxygen level between the exhaust side and the air reference side. In order to work, it does require a heating element. So within this matchstick, if you will, is a platinum resistive element. Works much like a toaster. It's just a resistive element. We have a validation protocol for testing the life of these resistive elements. For our automotive customers, the elements must survive 50,000 thermal cycles, 50,000, which really correlates to 50,000 keons on the vehicle at 13.5 volts. Now the problem with that is that 50,000 thermal cycles, and these are 1 minute powered on followed by 1 minute power off with fan cooling. I think in the pictures you probably can't make it out well, but there's a small muffin fans behind each of these banks of elements. So we do on occasion test these at nominal conditions at 13.5 volts, and it does indeed take 3 months, but we've also developed accelerated models so that we don't have to do this each time. In this particular example that I'm showing here, we tested 10 pieces each at 4 different voltage levels, and you can see the voltage levels are quite high. We measured the resistance once a day, every day, and the criteria for failure was if the resistance of the heater was greater than or equal to 10% of the original value, that was considered a failure. Okay, so this is kind of a noisy graph, especially if you're not used to seeing it. This was actually created with Alta, which is a program that Reliasoft makes, the same folks that do Weibull++. It's a little bit truncated here, but down in the bottom right, you can see the PDFs or the distributions and times to failure at each of the elevated stress levels. And then in this case, we chose as our stress voltage. And then the y-axis is, as you can see, is cycles to failure. At 13.5 volts, this is a log scale on the y-axis. At 13.5 volts, the cycles to failure would have been pretty large. But instead of running at 13.5 volts, we can now use this model. The inverse power law was used with voltage, and we modeled or projected what the B10 life would be at nominal conditions, and then we also have confidence bounds on that. So with this, you can see that there is we've demonstrated some margin, a considerable margin to our requirement, which was 50,000 cycles at 13.5 volts. Okay, so that is accelerated life testing, as opposed to MEOST, which I'll talk about next. MEOST, you can see there's our operating rectangle again, and it's labeled as 100% on the stress axis, but think of that as perhaps your 97.5 percentile condition. When you test at that condition and you test it to 1 life, if you're reading from left to right on that horizontal arrow, in many cases, especially when I found this to be very useful, is on new product that you really don't have an idea of how long it will last. If you kept testing along that horizontal timeline at the standard test conditions, you might test for a very long time before you get failures, and in a lot of cases we just can't afford to or don't want to wait that long. So what we would do then is, after you've demonstrated one life on test, we are going to increase the stresses stepwise between the normal conditions that we test under, which, like I said, could be 97.5 percentile or whatever it happens to be. We're going to step the stresses from there up to the destruct limit, which some folks also call the foolish failure limit. The easiest analogy there is the destruct limit for temperature with an electronic component might be the solder melt temperature. At the solder melt temperature, your solder is going to be pouring out of the test chamber. So you might think of that as a foolish failure limit. So certainly if you design your test to step up from standard normal test conditions to the foolish failure limit, if you have defined your foolish failure or destruct limit correctly, you will indeed get failures. So there's no guesswork. You will indeed fail your parts in that interval, in that that vector that goes from one life at standard use conditions up to the destruct limit. On the y-axis, the stress axis, it can be a single stress, but what's the real power for a MEOST is in combined environments. When you have combined environments, as I mentioned earlier, you more often get into relevant, field-relevant failure modes. But it does not have to be a combined environment, but that is where the real power of this is. Okay, the MEOST is primarily qualitative, but if you follow some of the rigor, there's some rigor that I'm going to show, and it's a little bit tedious, but not horribly so. This can be made semi-quantitative. You can do make reliability statements based on the results of the test. MEOST is a good alternative for new product lines or significant product changes when failure modes are uncertain and failure times are uncertain. It's especially a good choice, I found, for situations where parts are hard to come by. Either you just can't get them because of the tooling issues, or they're very expensive. So instead of testing a handful of parts at several different stress levels in order to build your model, you can take one set of parts, whether it be 6 or 8 or whatever the number is, and run them on your standard test, and then step stress them to failure. Now, there are a number of people that do MEOST that insist that it needs to be done on special equipment, on fast ramp chambers and pneumatic shock equipment. But I guess I'm here to tell you, and the perspective that I have is that you can very usefully administer a MEOST test on standard equipment, and we have. So the process starts by first defining the operating rectangle for each environment. So that's I guess I've got it labeled 1 down here. After you've defined the operating rectangle, you define one life on test, and in a lot of cases that's already done. You start with a well-accepted, well-correlated validation test, for example. In other cases, you have to go out and do the legwork to define it. But once you do that, the next step is to define or establish the destruct limit, or the foolish failure limit, for each of your environments, whether it's temperature or pressure or vibration or whatever. After you've done that, we need to define the overstress levels. The step, you want to define the steps. So each step has a time increment and a stress increment, and so we want to define those. And then you conduct the test to failure, and that the whole method sort of assumes that getting to one life at within the operating rectangle is not a problem, and if you do fail within that interval, then you just fix the part and go after it again. But what we're really going after is, after you get to one life, what is our margin? So we head up along the vector of step and time, stress and time steps. And if you follow the rigor, you can actually make wobble plots. And really, the short answer is the reason, or the way you can get to that, what allows you to do that, is that you normalize the x and y axis that you're looking at here. You normalize your time axis so that the time scale is equal to 1 at one life, and you normalize each of your stress variables to be equal to 1 or 100% at the level of the operating rectangle. But we'll get to that. Okay, so within the operating rectangle, this is really all about defining your basic test. Which environments do you want to include? You need to think about which failure modes do your risk assessments say you might need to be concerned about. On a new program, you don't always know what those are, even with your risk assessments, of course. So in such cases, you have to think about, well, what are the environments that my product's going to be exposed to? So, the more stresses you choose, the more likely you are to find your field relevant failure modes. What you're fighting against, conversely, then, is that each environment, of course, adds complexity to your test plan and your fixturing and test equipment. So it's a little bit of a trade-off there. So to define, steps 2 and 3 on this page of defining your rectangle, these apply to any test that we're going to define. You go out into the field and instrument your parts, and you record data. You instrument your vehicles if you have cars, for example. And you gather data on each of these environments on your parts. And you use that data to create the histograms excuse me, for each of these environments. And you choose a design level. You might choose the 97.5 percentile user to be the level at which you run your test. That's what we're going to call the design level. Okay. So then within the operating profile, I guess one thing you have to get your head wrapped around is within the profile, you do have cycling. So it's not, you're not always running at the, for example, at the high temperature end or at the high pressure end. In some cases, if you want to think about it this way, the 97.5 percentile stress might be that you are actually cycling between a high and low temperature or high and low pressure, for example. So you do have actuations or environmental cycles going on within the rectangle. Okay, I won't spend any time on this really, but these are a list of potential environments to consider. I do want to mention we do in terms of designing a MEOST, we think of temperature as being really, there's two different ways to think of temperature. You have a high temperature environment and a low temperature environment. Your high temperature cycles between, say, ambient conditions and some high level, and in some cases a low temperature, negative 40 C or negative 60 C might actually, the lower you go, the more damage you impart on your parts. So that is actually treated as a separate environment. You can have mechanical actuation, power cycling, and so on, but you just keep in mind that as you add environments, as I said, it increases the complexity of the test. Okay, so we start with, I like to start with 10 to 12 samples. That, of course, depends in large part on many of the practical factors involved with your project, cost and availability and so on. But if, let's say you start with 10 to 12 samples, because you can create a pretty good Weibull plot from that number. You run those parts for one life within the operating rectangle, and my note there, you should expect to pass. What I'm referring to there is if you don't know that you're going to pass even one life at your design level, if it were me, I would test fewer parts and try to find and fix problems before you commit to a dozen samples for one life. Okay, and then once you run to one life, you proceed to step stress testing with those same parts. Okay, so we've defined the operating rectangle. We have we want to now define the destruct limit. That's it's also considered in some cases by some folks a foolish failure limit. It's the stress level where a product can be expected to fail with a high degree of certainty. I mentioned solder melt temperature. That is a classic destruct limit for temperature. If you don't have solder in your product, perhaps you have plastic, and case melting at 180 C is an example I'm showing here. Those kinds of things, especially the temperature related ones, you can sometimes find just by looking in a handbook. For other environments, I list here PCB cracking at 10 Gs RMS. Well, you're not going to find, for your product, you're not going to know that that's the destruct limit for vibration on your, without testing that. So some cases you have to do some single environment testing, and I've done this with vibration, where we put our parts on a shaker and we tested them at what we considered the worst case orientation, and we ran the shaker up until we found the destruct limit, and that's what we used for designing our test. Okay. In some cases, and this has happened to me as well, the third bullet here, it's difficult or impossible to determine the destruct limit. We have had situations where, all right, we're designing our MEOST and we wanted to come up with the destruct limit for vibration. Well, we ramped up the shaker, and pretty soon we ran out of shaker and the parts were still fine. So we had to cap off as a practical limit what we could consider as the destruct limit for that environment, vibration. And what you're going to see shortly is that in some cases that does compromise the integrity of your test plan, but in other cases it does not. And you're going to see the example I'm going to show is one where we're not able to find the destruct limit for vibration, and it turns out it did not impact our test plan at all. Okay, now I'm going to talk about defining the step sizes in terms of the stress interval and the time interval. And before I do that, I did want to point out the very common misunderstanding with MEOST, especially for anyone that's maybe not real closely tied to it, someone that hasn't maybe designed it but has just witnessed the results. For example, if you're in the test world, one of your product engineering customers, those kinds of folks quite often make this mistake. It is not appropriate to overstress each environment all the way to its destruct limit. Even if you can, you do not want to do that. If you look at the example I'm showing for a particular product on a particular application, let's say this is just a contrived an example, but for temperature was measured and found to range between what we call an easy level of 23 and our design level. Let's say it's 98th percentile or whatever. We had some distribution of temperature between those values, and let's say we also know that the case melts at 150 C, so we know what the destruct level is. And what you can see, and this is sorted to scale, what you can see is that under normal conditions at the high end of our stress range, we are actually quite close to the destruct level for that environment. Now that is as opposed to in vibration, the range of vibration that's measured on our part on application is very small, and it's actually quite far away from the destruct level. So what you can see then is that under normal conditions, we're not anywhere close to failing. If you think about it purely in terms of vibration, we're not anywhere close to getting to our destruct level for vibration. So I guess what I'm getting at is if we were to just arbitrarily step these two environments between their design levels and their destruct levels in 10 equal steps, that is not something you want to do, because you're going to be overemphasizing vibration, where in the field temperature is more of a concern because you are closer to its destruct limit. Okay, and in the math I'm about to show, which is quite simple, will prevent you from doing that. So the percent overstress, and this is really the step size, so think of this as a step size, is really delta 1 divided by delta 2 times 100. So you can see delta 1 is the size of, it's the difference between destruct limit and design limit. Delta 2 is the difference between design limit and the easy limit, and times 100. So this is the size of the steps, as I said. We're going to compute this delta 1 over delta 2 for each of our stresses, and then we're going to compare the numbers and use the lowest percent overstress and apply that to each environment. So if we consider, once again, this is a contrived example. We have an operating rectangle, standard validation test that cycles temperature between minus 40 and 115 C, which are the values from the previous page. We have a vibration profile with an energy of 3.2 Gs RMS. And we have the test, we run the test normally up to one life being 400 hours. So, I'm listing under number 1 there, our stresses. Our high temperature between easy and design limit is 23 C to 115 C. For vibration, easy, of course, is 0 up to 3.2 Gs. For low temperature, you notice I'm not doing anything with that. We're going to hold that at minus 40. We consider temperature cycles to be important, but in this particular contrived example, cycling below minus 40 doesn't contribute to our mechanism of failure. And so also for this contrived example, our high temperature destruct limit is 150 C, and for vibration it's 15 Gs. So if I compute overstress, which remember is the delta 1 over delta 2, I get 38% on temperature and 369% on vibration. And what I want to show, 38%, if you look at these charts, it's really, think about the difference between 150 and 150 and 115 here is basically, think that's about 1/3 of the full range, my delta 1 here. That's about 1/3 of this range. In the case of vibration, the difference between 3 and 15 is 3 or 4 times the range of the delta 1 here. So for that reason, we are going to choose the lowest percent overstress, this 38%, to design our step size. And in this case, in this example, we're going to do our step stress testing in 10 equal steps. You do not have to use 10. You can use any value you want. The more steps you choose, the more discrimination you get. But in this example, we use 10. So if 38% is your overstress value, then what you're going to use is a step size of 3.8% for each stress. So here I'm computing the step size for temperature, vibration, and we have to do time as well. So there's our 38% divided by 10, so this is our 3.8% step. And that's 3.8% of the operating range, which is that delta 1. And we're going to, our step size for vibration will also be 3.8%. And our step size for time is 3.8%, leading to 15-hour time steps. And that is shown graphically here. Each stress increment is 0.12 Gs and 3.5 degrees Celsius. And each step is also 15.2 hours. Okay, and then when we get through our 10 steps, at the very highest stress step, we are going to be at our destruct limit for temperature. We will not be at our destruct limit for vibration, and that's appropriately so. We are going to be up to 4.4 Gs RMS. And when we're all done, we've tested 400 hours in our operating rectangle, and we're going to test an additional 152 hours in this case. So we have a 552-hour test. And at the end of 552 hours, we will indeed have failed each of our parts unless we've suspended the test ahead of that. Okay, so we do want to conduct a test of failure and plot the results on a Weibull plot. So let's talk about that. How do you make a Weibull plot of your failures? And you do need to think about why this is really a little bit of a leap here. Normally, when we run a test, we fix the stress level, and we just run until we get failures. So our x-axis is time. Now the problem with doing this with a MEOST is after you've exceeded your operating rectangle, after you get to this point, and you head up on your vector, you're not only increasing time with each step, your stress is increasing. So you have a sort of confounded situation. You're not, as you go on with time, you're having failures, but your stress is increasing as well. And the way this is treated, as I mentioned earlier, is by normalizing, non-dimensionalizing, if you will, your time and stress axes. You set your time value to be 1 at 1 life, and you'd set your time value to be 1 at, or 100%, at your design level. So let's say each 0.1 increment in time is treated the same as each 0.1 increment in stress. And once you've done that, that allows you to go up any stress time vector, or this stress time vector, and that then is the x-axis on your Weibull plot. And so what's shown on this particular Weibull plot, and it happens to be shown at 1% failure or 99% reliability, that is your goal, your target. So this black dot that's shown here on this graph is shown at 1 life. We want 99% reliability. And we can then plot our distribution of failures on this Weibull plot, and in this one we've even shown a confidence bound. I don't know which confidence this one happens to be, but you can see that it's still to the right of our requirement. So at whatever this confidence is, you can say that we've met our requirement. And there's and it also gives you some idea of what your margin is to that requirement. Okay, so as an example, Delphi makes a probe air meter, and you can see the picture of it, and then right below the picture of the air meter you can see the air meter mounted in a vibration fixture. It happens to be there's an electrodynamic shaker below this fixture, and the fixture is contained within a thermal chamber. So we call this our hot vibe test. So we're getting thermal cycles, normally -40 to 125 C, and normally 3 Gs RMS with a frequency spectrum that is characterized as our underhood, or it's a chassis profile. And we run this for 6 hours per axis. So it's an 18-hour test after rotation. The problem with this was that we rarely failed this test. I guess that's a good problem to have, but it does not allow us to look at weak failure modes and demonstrate margin. So we decided to conduct a MEOST, a step stress test using MEOST methodology. So we considered the stresses, of course, are pretty obvious. We chose high temperature. We actually went out thermocoupled. We were most interested in the electronics side of the air meter, so we put thermocouples on the circuit board and went out and recorded field temperatures on the circuit board. And we found that we ran these thermocouple parts on vehicles at our customers' proving grounds under a variety of driving conditions. And we found that the 97.5 percentile temperature was 65 degrees. Now, for anybody that's had any experience with underhood automotive, that might seem very, very low. But I can assure you that value is real, and it's really what it reflects is the fact that an air meter is in the intake stream. It's in the intake stream, so it's under constant cooling. It's got built-in cooling. The only time it doesn't have the cooling is after you turn the vehicle off and you park it, you get some heat soak, but otherwise you've always got airflow. The destruct limit for temperature was we used was the melting point of our eutectic tin lead solder of 183 degrees C. For vibration, we started at our normal use level of 3 Gs RMS, and we ran our parts up to the limit of the shaker. The limit of the shaker with the fixturing that we had was 38 Gs, and at that point we ran out of shaker, and we're scratching our heads, how are we going to deal with this in terms of the design of the MEOST. Well, as you're going to see, that it really didn't, our standard use 3 Gs is so far away from 38 that that could have been 138 and it wouldn't have mattered. You'll see that, I think, on the next slide. Yeah, we did not consider low temperature. We just kept the low step at -40, and just kept increasing the high step. So we got our delta T increases that way, and we did not comprehend humidity based, this happens to be a product we had in the field for a long time as opposed to new product program. So we happen to know that humidity related failures were not a concern. So if calculating using the rigor delta 1 over delta 2 formula I gave you previously, we computed the percent overstress for temperature and vibration. And you can see for vibration the overstress increase was 1,100%. That's based on 38 Gs. So let's say that the real destruct level for vibration was 60 Gs. Well, all that would do is drive that 1,100 to something even higher. And because temperature was our lowest overstress level, vibration, not knowing the vibration destruct limit didn't impact us. So our step size then is driven by the 274%. We decided to run the test in 10 equal steps. So what that amounts to is each step was designed to be 27.4% increase over its operating range. So for temperature, the operating range was 43 degrees C, that is between 22 and 65 C. We increased that in 27% increments, so each step size then was 11 degrees, 11.8. And likewise for vibration, we increased the step size for vibration was 27.4% of, in this case it turns out to be 3 Gs. So we had very small step sizes for vibration. And our time increment was also, our time step was calculated as 27% of the standard operating rectangle. So its step size was 1.6 hours per axis, or just under 5 hours per each of the 10 steps. Okay, so we took 9 parts and ran them on across the operating rectangle. We rotated those every 6 hours. We ran our 18 hours. And then we ran our step stress, our MEOST, according to the step sizes I showed. And we rotated parts every 1.6 hours. So this was actually pretty labor intensive. It required a person there pretty much all the time. And I kept them pretty busy. Okay, and we continued to increase the steps until we had failures. So you can see in this case, I guess the short answer is easy to see, and that is that we have considerable margin. We ran very close to our destruct limit for temperature before we got our first failure. And you can see in the table that if you're interested in making Weibull plots, the x-axis is either of those stress time columns. You notice that they're normalized to 1, so stress and time are both start off as a value of 1. And then you can see our 27% step size increments up from there. So that's how we annotate our x-axis on the Weibull plot. And I recorded serial numbers for what we called first anomaly, the first time we had any kind of electronic issue. We noted when that occurred and in which step that occurred, and you can see where they occurred. So finally, we plotted this. I've been talking about Weibull plots, but we actually chose a log normal distribution. And for those of you that have done Weibull plots, you can see it's maybe a little difficult to see, but these were actually this was interval data. We actually did not get precise times to failure. We just knew which step that they occurred in. But and then you can see I put a black vertical line at the foolish failure limit. you know, by definition we were not going to be able to get any further past the destruct limit. So on a Weibull plot, there is a point in stress time, if you will, beyond which you just, you know, are not capable of exceeding. So you can see we're a whole lot closer to that than we are. Our requirement, our red dot here shows that we required at one life a 99% reliability. So with confidence bounds on our data, then you can then examine what where you stack up relative to your requirement, and you can with different levels of confidence you can determine what your margin is to your requirement. Okay, one last example. This is a fuel injector MEOST, and I think what's really unique about this, I'll try not to spend too much time on the detail, but the unique thing about this is its simplicity, and what I'm talking about is this is a one environment MEOST. And you'll find, and I found, I've done a number of these as well, that these are also very useful. In this case, our Multec fuel injector was pressure cycled between 3 and 250 bar at a fixed frequency under ambient temperature conditions. Our standard life on test, our operating rectangle, is 10 million cycles. So there's two things we wanted to accomplish with this test. One is we wanted to compare two different prototype designs. So there was a prototype A and a prototype B, so we wanted to be able to run those to failure. We were not getting failures on the standard test, as I understand. So they chose to run a MEOST to do this. So as I mentioned, it's a single environment test. They chose pressure. The design limit was chosen to be the customer requirement, which is also their standard test value, 250 bar. The destruct limit they determined to be 600 bar, and they based that on the material properties within the fuel injector. So they tested 6 pieces each of 2 different prototype designs. They ran the operating rectangle for 10 million cycles, and within the operating rectangle the parts were cycled between 3 and 250 bar, and then eventually that high end, the stress level was increased. So 3 to 250, and then 3 to 300 bar, and so on as you stepped up. In this case, I don't think I'm showing the math, but they chose for simplicity to increase do their MEOST in 7 overstress steps. So their step size was 50 bar and 2 million cycles. Okay, and then this is sort of a cartoon that shows, all right, where did the parts fail? They exceeded their one life requirement at 250 bar, and they stepped up in stress and time. And you can see where failures occurred, and there's also at some point they decided to suspend the test, which makes a lot of sense if you've already failed most of your parts and you're under a time crunch. You probably, if you failed most of them, you have enough data to create a reasonable Weibull plot, so it makes some sense to suspend. So this is, there's not a lot revealed here other than you can see the stress time percent scale with the one life requirement. Prototype A actually had some major problems, and prototype B showed, even with the confidence around the confidence bounds around the data, still showed not a whole lot of margin to requirement, but certainly some margin to the results from prototype A. Okay, and then finally just a single slide on halt methods. HALT is a method, I think, that's primarily seen in the electronics industry. It's a methodology that uses very special equipment. There's special, very fast ramp rate temperature chambers on the order of 45 or 50 degrees C per minute with nitrogen cooling. So they get their ups and downs in temperature very fast. Vibration is conducted with pneumatic hammers, repetitive shock equipment. They get a broad frequency range with the high energy as well. As I understand, it's most often done with a temperature cycling and vibration, as well as in some cases power cycling. And then less often, but still, they still do this. You'll see humidity and even mechanical actuation, I believe. The HALT methodology is one such that, you know, because of the equipment, the test can be started and finished in 1 or 2 days. And the principal idea with HALT is that you're starting with just a few samples, a few electronic assemblies, and you run those to failure as quickly as possible. And when you find your first failure mode, what you do with HALT is you repair the part. You either replace the failed component, or you patch it, or somehow you fix your product so that you can put your product back on test, continue to run the assembly, such that you can find the next weakest failure mode, and so on. So with very few samples, maybe 2 or 3 samples, you can learn about all of your failure modes, not just the weakest one, like with a MEOST, but you learn about all of them. The downside is the equipment cost, as well as the fact that you are not you don't get any kind of quantitative reliability demonstration. This is all about finding failure modes on projects that are very early in their development stage, as opposed to as I said, no kind of reliability demonstration at all. So I think that's it. I guess I'd be interested in any conversation or questions on MEOST, maybe in particular on how I applied it, as opposed to maybe what you've heard or what you're familiar with, or anything else.
Well, thank you, John. That was a great presentation. Once again, if you have a question, please type it in the question panels on the chat there, and I'll get them to John. John, we have first question. How do we get the normal stress level? Do we get the data from the customer usage or engineering assumptions?
Well, all of the above. The best way to do it, and I'd be less than honest if I told you that I did it this way every time. But the best way to do it is to instrument your parts. I mean, basically the same question could be asked of how do you design any test, any relevant correlated, field correlated test. Well, the best way to do it is to instrument your components and run them on your intended applications under a variety of representative driving conditions and environmental extremes. And then so you end up with time versus temperature plots, or vibration G levels, vibration versus time plots. That's a little more complex with vibration, but you end up with your histograms, and and then from the histograms you can pluck off, say, your 97.5 percentile value for temperature, vibration, pressure, and so on. Now, what's on the other extreme, if you're in a real-time crunch and you're more interested in, and you get more towards the qualitative side as opposed to quantitative, you know, some folks are just, the easy way out is to pick the, you know, they have no idea, no parts available, no time to measure field values. You use what the customer tells you the usage level is. Perhaps you have an engineering spec. You use the value in your engineering spec. So, you know, those are two extremes. Hopefully you can err closer to the side of having some kind of field relevant data, but in some cases you have to compromise.
Great. We're about ready to run out of time, John. As long as the GoToMeeting webinar software doesn't kick us off, we'll keep going, but hopefully it doesn't drop us off. The next question is how do we estimate the design margin in the acceleration testing, and how do we use that margin that you have for cost savings?
The design margin, okay, if I understand correctly, we're talking about if you create a Weibull plot, let's say, of the results, and you're, I don't know if I can I do this?
Yep, no problem.
Okay. That's not a real good. Maybe the question is about, you know, in this particular example, there's a huge design margin between the requirement and where we ended up. I guess if I understand that correctly, that I guess what I would say is, you know, you get your engineers together and try to decontent your part. It's always risky, but the nice thing is MEOST is a fairly quick turnaround test, and you just test design alternatives that are decontented. Of course, you always have to be concerned about with the unknown, and you still have to validate with your full validation protocol, but I think I'd go about it that way.
Great. We have a couple questions in about can we get a copy of the presentation, and the answer is yes. I'll have that posted on our website on ASQ/auto.org. I should have the presentation up there by tomorrow. I'm traveling out of the country right now, so it's going to take me a couple days to get the recorded webinar up on the site, so look for that hopefully over the weekend if all goes right. Next question. This question came in during the electronic oxygen sensor example. What is the B10 life at the elevated temperature?
Is the question regarding what's the definite, what does that mean?
Yeah, unfortunately, John, that's all it says. I don't know if somebody wants to clarify that, but I guess give it your best shot.
Well, B10 life for any product is the life at which you'd expect 10% of that product to fail in, under those conditions. So the B10 life in the field is the time at which 10% of the product will fail in the field. B10 life on test, of course, means the time on test at which 10% of your product will have failed.
Great. Any other questions? I don't have any more questions in the queue. Okay, well, I'd like to thank everybody for attending. John, thanks again for taking your time. What a great subject. It was very technical, and I think with the questions coming in, it was a great topic. Once again, I have our website up, asq-auto.org. Like I said, John's presentation and the recording will be posted up there hopefully this weekend sometime. And hopefully you folks get a chance to come and join us on an upcoming webinar. I have on the screen our next few webinars. It's going to be on the automotive core tools November 9th at 7 o'clock, same time. We're going to have the PPAP, November 16th, the FEMA module, and November 23rd, the SPC module. And I'll have the registration on our webinar right under webinars here. I should have that up there by tomorrow, so feel free to register for our upcoming webinars. So, John, thanks again, and thanks everybody for joining. Good night.
Okay, good night.